Okay, so we've talked about the waves and electromagnetic radiation last time. And we talked about the different lengths. I have the radio waves and the electromagnetic spectrum. Right? There we go. So you've got radio. Then you would go to infrared. And then our visible light. UV, ultraviolet, X-ray, gamma ray. And you can see it's a continuous spectrum. It's that radiation that has that electrical wave and that magnetic wave that are inducing each other and keeping their strength and holding their strength because of that induced effect. So really, radio waves are the same type of wave as visible light, just a different wavelength. They're shorter. I'm sorry, these are longer wavelengths. These are the shorter wavelengths over here. No, it's not visible. But like infrared, the infrared goggles they use in the military, because heat is a form of infrared radiation.
So that's the heat signature.
Yep. So what they're doing there, well, heat gives off an infrared light. It's not necessarily heat itself, but it's a light given off by most heat sources, like the human body. What those goggles do is they actually it's a double polarizing lens. So it takes radiation coming in and it actually cuts the wave up and changes its amplitude and turns it into a visible form of light. So that's what it's doing. It's chopping up the wavelength. So radio waves, I suppose you could chop them up and see them, but it wouldn't be a radio wave anymore. Because technically what you're seeing through those infrared goggles is not infrared. It's been turned into visible light. Yep. There are several animals that can see UV. Most insects can, some birds. Infrared, they claim cats have a little bit more visibility into the infrared spectrum. Not true infrared vision, but a little bit slightly more into it. You have, so the visible light that kind of sits in there by itself. But the interesting thing about visible light, even though it fits into this spectrum of wavelengths, you got the longer wavelengths and the shorter wavelengths over here, it almost is kind of an entity in itself. You can almost pull it out on its own. You have red over here by the infrared and violet down here. There's actually a full spectrum of colors. It's red, orange, yellow, green, blue, and violet. Some of your color packs and rainbows include indigo in there. Indigo is just a blue-violet, and it's really not its own color. It's just thrown in there to make the Roy G. Biv thing work out.
And black color.
Black is an absence of light. You see black on that shirt because it absorbs all light and doesn't reflect any light.
That's why it's black things get hotter.
Yes, because they absorb all the radiation. White things reflect all the different colors of light. White light is just a combination of all the colors put together. So white things reflect all the colors of light, so they don't get hot. They don't absorb as much radiation.
So could we filter out like blue, violet, green, and get like red, orange, yellow optimals?
Yes. On Monday, I've got the color generators down in my classroom. We'll actually show you some of the color generators. And I'll show you how some of that works. There are two types of color theories. When we're dealing with radiation, actual electromagnetic waves, visible light, light is what we call additive color. Colors are formed by adding colors to each other. The three primary colors in additive color are not what you think. What were you always taught were the primary colors?
Red, green, blue, and blue.
Well, most of us were taught in art class red, yellow, and blue. But you're absolutely right. Red, green, and blue. RGB You hear about RGB monitor?
Yeah.
It's a red, green, blue.
Yeah.
Because that's generating light. It's lasers that are generating light in there. Actually, now they're not even lasers. They're liquid crystals. So anyway, those are the three primary colors: red, green, and blue. For additive color, for lights. And it's weird because even though they're in that spectrum, they kind of wrap around onto each other. If you think of a triangle with these three primary colors, we can put them wherever we want to: red, green, and blue, like this. We can then throw the secondary colors in there. I'm going to use black so I don't have any specific color in there. Red and green light combined to make yellow. Green and blue, now this is probably a color you haven't heard of before, combined to make cyan. Red and blue combined to make a color called magenta. And I might be wondering, where's the purple or violet, and where's the orange? Well, when we're dealing with additive color, those are... Yeah, orange is somewhere between red and yellow, but orange is not even a secondary color. It's called the tertiary color. It's a mixture of red and green with a higher proportion of red, or you can call it red and yellow. So this is the additive color wheel. Now, most people are not familiar with cyan and magenta. We'll actually show those in the lab on Monday, or in the classroom on Monday with the color generators. But again, these colors are formed by taking light and adding more colors of light to it. We also have something called subtractive light, or subtractive color, not light. Subtractive color is like mixing paint pigments. When you guys are mixing paints in the shop, you are mixing subtractive colors. Those pigments are designed to take white light coming from the sun and absorb certain colors so they're not reflected and not visible to whoever's looking at them. That's how illusion paints are done. Illusion paints are designed so that they absorb certain colors, but it's weird because certain colors, when it hits it directly, they absorb it, but when it hits it at a steep angle, it does not absorb it. So that means when you're looking directly at it, it's a certain color because all those other colors are absorbed, but when you're looking at it at a steep angle, those colors are not absorbed at that angle, so you see the other colors. So it appears to change color depending on what angle you're looking at it. Yeah, well, flop is actually a little bit to do with the metallics, the metallic particles. But they actually have paints called illusion paints that are designed to absorb colors differently depending on what angle the light rays hit them at. Yeah, like chameleon colors. They do have a new paint now. I've got to show you this. If I can find it. This is it. Have you ever seen this? This is actually an electrical controller.
Yeah, I showed us some of this. Like,
Did you show?
Color is being able to illuminate it.
Is that what it was?
They're putting it on bikes and stuff like that, and you get a switch and it's wired.
Okay. I've seen that too, where the paint lights up.
Instead of like glowing in the dark, it just has this color.
See if this one works. Okay, yeah, here, you're moving around the car. They just hit a button. And now it's green.
That's cool.
This is an electrical current. By sending a different voltages of electricity through the car, it changes color.
That'd be hard to find.
Be hard to match.
Now it's purple. It'd be a blast running from the cops. Now it's red, or now it's brown, actually, that orange. I think it's only 3 or 4 colors it would change to, if I remember right.
That's pretty.
That's cool.
But I always wondered how they did it because, most of these front effects are plastic. If they had to use a conductive polymer or whatever. That's cool. I have no idea the science behind what cause. I know it's the different levels of voltage that they send through it that cause it to change color. I have no idea how they actually design it. What's actually in the paint that causes it to change the color.
How, like, 'cause there's breaks between all the panels and stuff like that.
Yeah, it's got to be wired.
Send
So.
electrical currents through that whole thing. Yeah, you'd have to wire them all together. So.
Yeah. That would be cool.
You never call it a steel plate chicken spinner.
Yeah,
Give it all kinds of crimes.
if they ever inspected your car, you know what trouble you'd be in.
All right, Bob, you're going to jail. I got one from one of the bright colors.
Which one?
The
Oh, this one? Yeah, where the colors light up.
was that one movie? Tron.
Oh, yeah. That is kind of cool, too.
It won't be very long before they make that illegal because it's too much of a distraction or some shit.
Just like the undercarriage lights that they're supposedly illegal, but everybody has them.
You know, you can have them, but you can't operate. They can't be operated by
Yeah.
Let's go out the symbol.
Yeah. That's kind of cool.
No.
Oh,
That was dumb shit.
Yeah.
why would you rig up a... I thought that was a minivan. It's like, why would you rig up a mini? It's still ugly. I hate those cars, but this must be in Japan or something like that. Those cars are supposed to be really hot in Japan. I was gonna say, I thought it looked like a...
Looks like a Datsun. I think it's a Datsun. Well, it could be.
It's not a Mustang. The heck?
Well,
It's a GTR.
Is it?
Yeah.
That's gotta be a little hard on the tires. And the rear brakes. You don't want to drive that?
they don't make it mandatory because it's more safe if you sit in a whole car.
Yeah.
Yeah. So anyway, I wanted to show you that. It doesn't really have much to do with what we were talking about, but it's kind of cool to see the color changing car. But anyway, subtractive color, like I said, those pigments in paint absorb certain colors from visible light. So they're actually taking colors out of the light. When you mix them together, what you're doing is saying, okay, I'm going to mix this color, and they're going to take out both of those types of colors then from visible light. For example, the primary colors for subtractive colors are red, yellow, and blue. Just like mixing paint when you were in elementary school. So if we put those on here, we have red, yellow, and blue. The secondary colors, then when we mix red and yellow, we get orange. Yellow and blue mix to give us green. And red and blue mix to give us violet or purple. That's the color wheel we're probably most familiar with. Now, in either one of these color wheels, we have something called complements. It's more meaningful in the subtractive color wheel because complements are actually describing what the pigments are doing to the light. For example, the complement of red is green because green is exactly across from red in the color wheel. When you look at something and it looks red, I'm trying to look around the room and see if there's anything that's red in here. The ladder or this water bottle even kind of. When you're looking, or the fire blanket over there, that's definitely red. When you're looking at something and it appears red, what that means is that object, that paint, is completely absorbing green light from the white light that we see. If you put shine the green light on it, you wouldn't see it at all. It wouldn't show up hardly at all. It'd look black. In fact, when you do that, you take a light, would put a green filter over it, and you'd shine it around the room. You'd see some of the other colors. That would be totally black, or at least a very dark gray, depending on how pure the color is. Red light is totally reflected. Now, yellow light, since it's on sort of on the opposite side, close to green, is nearly totally absorbed. There may be some of it that's reflected, and most of it's absorbed. Same with blue. It's mostly absorbed with a little bit reflected. Violet and orange, maybe a little bit absorbed, but most of that is reflected, depending on how pure the color is. And we're going to talk about hue value and chroma in a couple of days. Chroma is the purity of the color. The more pure the color is, the more different colors of light it absorbs. For example, if that's a really, really pure red, it absorbs all of this and only reflects the red and the colors really, really close, the wavelengths really, really close to that red. If it's a sort of a washed out red, it might only absorb green and a little bit of the blue and yellow and reflect all of the rest of this. It still adds up to be a red, but it's more of a washed out, impure red. So it looks kind of the same at first, but it's not as pure, not as intense of a color.
What makes it, so if just what we see doesn't make something color, what makes it?
Well, it's what when your eye senses the wavelengths of light coming in. In fact, if you were to just put orange and violet light, just a very, very small slice of orange and violet together and shine it, and you looked at it with your eye, it would look red to you. But it wouldn't look near as pure or vivid as if you just took red light and shined it and looked at it. Kind of like...
Someone was telling me that when you see something, you're seeing every color but that. That's why.
No. It's not every color but that. It's that every color but that is being absorbed by the object. The reason you're seeing that color is that's the color that's being reflected. But again, it's not necessarily just that color that's reflected. When you see red, it could be just reflecting red. That would be a very pure red. But it could also be reflecting red, violet, and orange. But when you see violet and orange, your eyes just automatically combine them to make red, if they're in the proper mixture. If there's a little bit more of one or the other, well, then it's kind of an orangish red or a reddish violet or whatever. So a little bit off to the side. But the complement is still completely absorbed. For us to see red, green light is completely or nearly completely absorbed by that object. So if I was looking at let's say I look at something and it appears to be blue. What color of light is almost totally absorbed? Orange. That's the opposite. That's the complement, is orange. Red and yellow are probably mostly absorbed as well. The violet and green, depending on how pure, they can be mostly absorbed or they can be almost not absorbed at all. They'll still mix together to make blue. Again, it depends on how intense the blue. If it's a really intense blue, you're only going to get a slice of blue, a really narrow slice of wavelengths of color. If it's a more washed out blue, you're going to get a wider band of wavelengths. But it's still blue because whatever's at the center of that range of wavelengths is the color your eye senses and sees. It mixes them together.
So how do you make something reflecting light?
That's where the pigments come in, is you have to mix those pigments. And most pigments that you get, you don't have a whole lot of control over what you're getting for pigments. But the more you play with a color and adjust it, let's say you mix a paint and you do a test panel and hold it next to the car and say, it's a little too dark. Car's faded a little bit. So you go back, you lighten it up a little bit. You bring it, now it's a little too light, so now we got to darken it up. The more you adjust it, the more extra colors you add to that, the wider that band of wavelength starts to get, and the more, even though the colors may match, it's not quite as intense or pure.
What about things that are just not paint?
Well, there's still a pigment in them. Yep, even though they're not painted, there's still pigment in them that causes them to absorb those colors. That's really, that's kind of brings you into the whole, the theory of color vision and all that, is how those colors are absorbed and then how they mix together, how light mixes together and all that stuff.
Look like hair, skin color.
Yep, they have pigments in them.
What's the definition of a pigment?
Pigment is just anything that absorbs or reflects certain colors of light. Was it melanin or something like that in the skin? It determines how dark, when you're out in the sun a lot, it increases the amount of melanin. That's what gives you a tan. Stuff like that. I think that's the right word. I'm not, something like that. Google it. So when we're looking at light again, obviously the sun produces a full spectrum of light. The sun produces light from a process called hydrogen fusion. A pretty pure light source, full spectrum light source. There are other fusions other than hydrogen fusion. Our sun, we don't think, is large enough to sustain a helium fusion. The way suns work, or stars work, I should say. Gravity, of course, the more matter is in an area, gravity pulls the particles together. Well, if you take any gas, or any material for that matter, and you squeeze it hard enough, it starts to get hot. In fact, if I remember right, I'll bring in one of my liquid crystal thermometers, and we'll just take a pop bottle or something and slide it inside there, and you squeeze the pop bottle, you can actually see the temperature go up 2 or 3 degrees if you squeeze it hard enough. The more pressure you put it under, the hotter it gets. So you can take any material, if you can squeeze it hard enough, it will ignite. And that's what flash powder is. You ever seen magician's flash powder? You can actually take it in your hand, and it's close to room temperature, is close to its ignition point. So you just got to squeeze it a little bit, and it'll ignite. That's why you throw it to the ground. That little bit of a concussion puts pressure on it, and it ignites. Hydrogen has a pretty high pressure that it requires to ignite, but if there's enough of it there, the gravity of itself pulling against itself squeezes it tight enough so that it ignites. That's what's going on in the sun, is it's squeezing so tight that it's fusing those hydrogen atoms together, and it's causing hydrogen fusion. Well, hydrogen atoms each have 1 proton. They squeeze together, and now you got an atom with 2 protons, so it becomes helium. So our sun is slowly taking hydrogen and fusing it into helium. At some point, it will run out of hydrogen, and it will all be helium. What happens at that point, we're not completely sure, because we don't know if our sun is large enough to undergo helium fusion. We've seen other stars out there that once they've used up all the hydrogen, they kind of go through a process, a rapid expansion, and fall back into itself again. And then if there's enough helium there, helium will have enough gravity on itself to squeeze itself tight enough to ignite and cause helium fusion. Well, helium has 2 protons. You just put 2 protons and 2 protons together, you get 4, which now would give you carbon. It would fuse into carbon. Carbon is, what am I missing here?
They just start labeling those suns differently after they've
Yep. You hear about nova stars and dwarf stars and pulsars and stuff. Some of that has to do with what stage they're in, what stage of burning they're in.
That was a great series on the universe.
Yeah?
Discovery Channel. I love that show.
What am I looking at? Periodic table. Oh, there it is. Good. Number 4 is beryllium. So 2 helium atoms would combine to make a beryllium atom. And then 2 beryllium atoms would combine to make number 8, which would be an oxygen atom. So if there's enough of it there, you'd have oxygen fusion. And oxygen fusion would give you, well, 8 plus 8 is 16. You get sulfur. And I don't think we've ever found a star that's big enough to undergo oxygen fusion yet. I don't think so. But it's kind of neat. It would, theoretically, if there's enough matter there, it would just keep going and keep reacting and keep fusing until you got up to whatever. So anyway, other suns that are undergoing helium fusion, we don't know if they give off the same spectrum of light. So far from what we found, we haven't found any that are different, but we don't know for sure if there are other wavelengths of light out there that we just don't have because of the type of fusion our sun undergoes. But anyway,
Our sun's a little smaller.
our sun it's not tiny, but it's not big. It's in the smaller category. Yeah. Like I said, we think it's right on the edge. We don't think it's quite big enough to undergo helium fusion. But it wouldn't matter to us. We'd be dead anyway before it got to that point because that rapid expansion and contraction, they theorized it would flare out slightly past where the Earth is, so we'd get wiped out anyway. We've got a few thousand years before that happens, though, so I don't plan on living that long. Other light sources we have. There you go. Incandescent lights. Those are just your bulbs with little filaments in them that heat up. They produce light by sending electricity through a small filament. The resistance of the electricity going through that small filament causes it to heat up. It's that heat that causes it to glow. So they literally produce light from heat. That's why they're inefficient, is because most of the energy goes to producing heat and not producing light. That's why they switched over to fluorescence, because they don't lose as much of their energy to heat. Although some of the compact fluorescents actually give off more heat than incandescents, it still takes less energy to create that heat. Incandescents tend to be very, very heavy in the yellow and red colors of the spectrum. Depends on the fluorescence. Fluorescence, in a fluorescent bulb, there's a couple of different types. There's cool fluorescence, warm fluorescence, and so on. Your warm fluorescents tend to be into the yellow-orange range. Your cool fluorescents are more in the green and blue range. But they're just a gas that's excited. You send electricity into it, and it causes the electrons to move from one level to the next, and it emits photons of light. And it depends on what gas is in there, is what's the energy level difference between the electron energy levels. That determines what color of light is emitted. We'll talk more about atomic structure and electron energy levels in a few weeks, so it might make a little more sense then. But it's the electrons being forced up at levels and then allowing to fall back down that gives off the light. So those, it's all, yeah, it's kind of like a gravity. Think of there as being like shelves stacked up in this room. You can lift an object up a shelf. That's exciting the electron. Well, but eventually its gravity is going to want to pull it back down. And when it falls down, it emits a little bit of energy. And that's that little light pulse that comes out. That's why some of the older fluorescents appeared to flicker, because that's what it was. It was giving off little pulses of light. The newer ones, they use a mixture of gases in them and not just a single gas. So they're giving off those pulses at different frequencies, so they mix together and you don't see the pulsing anymore.
Neon's the same thing.
Yes, neon is similar, it's a different gas. Then they have vapor lamps. These are like your street lamps or vapor. And there's two types. There's mercury vapor and sodium vapor. Well, mercury is a greenish blue. And if you look at them, you can actually see the greenish blue. Although now they have the xenon that are very blue as well. Sodium is more of a yellowish orange. Well, it's more intense. It lasts a lot longer. In applications like streetlights or something where it's a real pain to get up there, they put them in because they'll last for years. They do take some money to use, or to operate, but they're just durable is the main reason for using them. Mercury vapor, of course, we don't use much anymore. There's still some out there because they last that long, but mercury is a very toxic chemical. It causes a lot of birth defects if it gets in the water supply and all that stuff like that. Similar to lead. LED is light emitting diode. It is actually usually silicone, germanium, or other what they call semiconductor materials. It's layers of material. What a diode is actually layers of material that are designed so that electrons or electricity can jump from one side to the other, but only in a single direction. That's why on a wiring diagram, a diode would look like this, because electricity can only pass through it in that direction. So there's what's called a reverse bias voltage or reverse bias critical voltage. If you apply enough electricity, enough voltage going the other direction, you can actually override that, and you can actually force electricity to flow through the diode in the wrong direction. An LED is a type of diode that when that happens, it emits a pulse of light. So you're overpowering the diode and sending electricity through it the wrong way. But it doesn't give off much heat, and they're very durable. So you'd think that'd be very bad for them, but it's not. They last a long, long time, 5 to 10 years.
It's really expensive for new LED lights.
Yeah.
Products.
Oh yeah, it's several $100.
Backtail lights for the charger or something like that.
Yeah, that's because it's a solid panel all the way across.
Yeah.
I know just for like a regular, they have the kit to convert your regular tail lights over to LEDs. And for a lot of your trucks, just that tail light like this is like $400 or $500 per light. One of the problems they had with LEDs at first when they came out with them, by the way, was an LED tends to emit light straight down like that. So now what they do is they've got an array of LEDs lined up, a very complex array of LEDs. So they shoot light straight out, but they got enough of them in there arranged at enough different angles that it still gives you a pretty even spread. Because an LED light, even though it had no constrictor cone on it, like that's what spotlights do, is they have a cone, a parabola on them that focus the light. An LED, you put an LED up there with nothing around it, and it would still just form a spotlight right on the table surface. So they had to put them in an array like that so they shine in different directions so you get an even light throughout the room instead of just a bright spot. So we talked about reflection, refraction, and diffraction. Talked a little bit about trying to spear a fish in the water. Pretend that looks like a fish. If you're standing over here and you're trying to spear that fish, you're going to be shooting high pretty much every time. Because the light coming off that fish, it's going to hit the fish and it's going to reflect it at the same angle. But when it hits the surface of the water, when it hits the air, it's going to travel faster through the air. So that light is going to curve this way. Because this side of the light wave hits and speeds up before the bottom side does. So it curves. So what you see, it looks like the fish is over here. So you've always got to shoot low when you're doing that. Unless you're coming at it directly from above, you're going to have to shoot low. On the Earth, let's say here's a sunset, and those sun rays are hitting the Earth. Well, the Earth, of course, has an atmosphere around it. So when the sun rays hit the atmosphere, it's going from no medium. Remember, electromagnetic waves are the only type of wave that does not need a medium. It's going from having no medium, no air, ether, hitting the air of the atmosphere, and it causes them to bend a little bit. And remember, we said that a red light bends more than the violet light. Violet light doesn't bend much at all. So since the red light bends more, it stays in the atmosphere. So somebody like right here on the Earth will see the red light because it still bends. The purple light keeps going straight, and the direct light that would have come in and hit it directly with the purple is already blocked by the edge of the Earth.
So that's why you see it's purple.
That's why your sunset will start out, solid, then it'll start to go kind of a yellowish, then orange, and then red right before the sun sets.
Why are the clouds purple?
Clouds purple? Well, because
Purple is huge.
I said that purple and blue don't bend much. If you're looking at the atmosphere is full of droplets of water, right? Every little droplet of water is like a little prism. So the red light hits those and it gets bent off, like that. The blue and purple light hit it and they don't bend hardly at all. So what happens is this white light is shining in that has all these different wavelengths of light. The red light is more likely to hit a water vapor and get bent off to the side. The blue light's more likely to just go straight through. So there's a higher percentage of light hitting the earth that's blue than it is red. That's why the sky looks blue. And that's also why the water looks blue, is because the sky is blue. It's just reflecting the sky. Any other questions? I think that's a great way to end the day right there. Talking about something.